Please allow me to introduce our presenter. Cary Sneider is a lead writer for the NGSS as well as a research professor at Portland State University. Cary, the stage is all yours.
Thank you, Ella. Could we go to the first slide? I'm seeing the resources there. That'll help.
Those are important. There we go.
Well, by the way, while Ella's finding the first slide, oh, here we go. Every now and then you'll be meeting my my cat Gibson, who's curled up right next to me. It's in the 20s today here, so it's warmed up quite a bit from last night. But he really likes the warmest spot in the house, which is right here. So today's presentation is called What to Do with Cross-Cutting Concepts. And I wish I could tell you I have all the answers for you. Frankly, understanding what to do with cross-cutting concepts is a work in progress, although, as you'll see, it's not a new work. There's been efforts to really introduce these ideas into science education for the last 30 years. And a lot of work still needs to be done. And I'm hoping, while I will share certainly what my ideas are about that with you, I'm hoping some of you will come up with your own ideas and publish some of them in the NSDA journals or other places for teachers and teacher educators, because there's still a lot to learn about it. So let's advance to the first slide. And the first question is, what are cross-cutting concepts? We do need a slide, though, Ella. Would you go to the next slide? Here we go. So 1989 was the first really well-known call for cross-cutting concepts. But the idea actually came a few years before that. California had a science framework prior to Science for All Americans, which identified about 20 of what they called big ideas in science. And I'm not going to read this for you, but I want you to take a second and read this short paragraph from the AAAS. The idea is that cross-cutting concepts are really important concepts in science that aren't tied to any one particular area, but in a way describe the way scientists and engineers think about the world. And in a sense, one of the major aspects of nature of science is really the way these cross-cutting concepts can be applied. Let's go to the next slide. I think one of the best ways to define cross-cutting concepts is in terms of what they are and what they're not. So a cross-cutting concept can be applied to all different disciplines of science. The idea of Newton's laws, although they may be appropriate in different fields, really don't apply to all different fields. Even the particulate nature of matter is a core idea about the nature of matter, and it applies in biology, but it's not very helpful in the areas of astronomy or zoology. So, so cross-cutting concepts apply to many different disciplines, and they're a scientific way of thinking about a subject. A concept is not cross-cutting if it can only be applied in one or two disciplines, or does not communicate a scientific way of thinking. Now, that second bullet in both cases, I want to admit, is a bit circular. So if we say that a part of the nature of science is cross-cutting concepts define the nature of science, and then we say that we're defining cross-cutting concepts in terms of scientific ways of thinking, it's a bit circular. So another way of thinking about it is that you know and you see it. What the framework did, that's the framework for K-12 science education from the National Research Council that defined these, simply took the task of identifying 7 cross-cutting concepts. Let's take a look at the next slide. Now, historically, there have been a number of different cross-cutting concepts identified. Science for All American had a set, the same set as what we found in the benchmarks for science literacy. The National Science Education Standards in 1996 presented a slightly different set. For the most part, they're really similar, all these different ways of thinking about cross-cutting concepts, and they're typically presented in pairs, such as cause and effect, scale, proportion, and quantity. So the first one, patterns, you can think of as perhaps the simplest one, and perhaps the way science actually began when people started noticing patterns in the world around them, and then they started noticing that some things cause other things. So there's somewhat of a progression to those ideas, but for the most part, they all remain very important ways of looking at the world and trying to understand them from a scientific point of view. So these are the 7, and we're going to be talking about all 7 during this webinar today. Let's go on to the next slide, please. There we go. So the first thing I wanted to describe to you is how the cross-cutting concepts are integrated into the next generation science standards. And the core of the NGSS are these statements called performance expectations. And these performance expectations will become essentially the heart of the next generation science standards. These are the statements that will help people organize curriculum, instruction, and assessment. What they are really supposed to represent are endpoints of instruction. So this example, for example, for a 3rd grade student is that all students are able to, after instruction, represent data in tables and graphical displays to describe typical weather conditions expected during a particular season. So, and of course, the goal of teaching is to guide students through a series of experiences so that they can do this at the end of instruction. So the first part of it that's in blue is a practice. And again, practices also cut across the different fields, but they represent not an idea, but a capability, something students should be able to do, represent data in tables and graphical displays. Let's go on to the next slide. And the next slide emphasizes the core idea. So the core idea in this case has to do with weather. And so students are expected to describe typical weather conditions expected during a particular season and to use the practice of representing that data in tables and graphical displays. So the idea is that you don't assess these separately from each other. You don't assess their abilities to use data in tables separately from their understanding of weather conditions. You assess them together. And now the third dimension is cross-cutting concepts. And notice what happens to the colors. That second phrase, describe typical weather conditions expected during a particular season, is not only a core idea, it is also a cross-cutting concept of patterns, because to describe typical weather conditions is a pattern. And again, these 3 are expected to be assessed together. You'll go a little crazy if you try to think about assessing each one. But if you assess the statement, can students do what is described here, then they are being able to accomplish all 3. So, so the idea of eventually, as we come to be able to develop assessments that assess students' understanding or their ability to accomplish these performance expectations, we'll start getting used to the idea that they represent all 3 dimensions. Now, that doesn't say how to teach it yet. We're going to get to that. But this is how it's integrated. So what I'd like you to do, Ella, is I'd like you to toggle back again to dimension 2 and 3 and notice how this same phrase in this particular case refers to both. Notice it doesn't actually say the word pattern. So the idea is that in interpreting these performance expectations and trying to ask yourself the question, what is the cross-cutting concept here? Some cases you'll actually see something referring to pattern or stability or form and function. But usually it's a matter of looking at the statement and saying, which of the 7 cross-cutting concepts really apply here? So let's move on now. Go on to the slide after this one. Next slide. Okay. So what I'd like to do now is go through each of the cross-cutting concepts and with some examples. Now, the examples I've chosen are elementary, but these apply just as well at the middle school and high school level. The idea of them really is very similar. So for the first one, patterns, observe patterns of forms and events. So these are not just a pattern of objects that you can look at, but patterns in time as well. They guide organization and classification and prompt questions about relationships. And in a sense, this is the way science, new sciences really start. People start recognizing similarities and differences, eventually leading to understanding about relationships. So an example, for example, is this kindergarten example, that students are expected to use observations to describe patterns of what plants and animals, including humans, need to survive. So, for example, all animals need to eat. They reproduce. They need to drink. They need to breathe fresh air, and so forth. So simply understanding those commonalities are important. But this is just as true at a high school level. So students at the high school level who are studying galaxies, for example, see the similarities and patterns among galaxies, which eventually lead to an understanding of how galaxies evolve over billions of years of time. Let's go on to the next one. Slide, please. Okay. So cause and effect. And in a sense, this is something when we think about science, we think of as, well, this is science, understanding how the world works. So, for example, in this case, the example of a performance expectations is students are able to plan and conduct investigations to provide evidence that vibrating materials can make sound and that sound can make materials vibrate. The first part of it seems pretty obvious. You could feel, as you speak, the vibration. But the idea then that that vibration turns back into sound is a little more complicated idea. Still, within grasp of first graders should be able to do that with some experiences, with some hands-on experiences and opportunities to reflect and discuss that. So again, wherever there's effect, you can look and understand the cause. And understanding that cause and effect is the process of explaining. But the idea that these causes and effect exist, that is the cross-cutting concept here. And you'll find a very large percentage of the performance expectations have this structure where there is a cause and an effect, and understanding that cause and effect. Keep in mind the idea that you don't assess this separately from the core ideas, so that you see cause and effect in this case with regard to sound, but you also see it with regard to life sciences, with regard to chemical reactions, with regard to physics. Again, not all of the performance expectations, but many different ones. So let's go on to the third one. Next slide, please. Okay, scale, proportion, quantity. Basically anything having to do with numbers, with ratios, and with scaling. And actually, scale, proportion, and quantity covers quite a bit of ground. So there are a number of different types of performance expectations that fit this cross-cutting concept. But the main point here is it has something to do with amounts. So this example is that students should be able to measure and graph quantities to provide evidence that regardless of the type of change that occurs when heating, cooling, or mixing substances, the total weight of matter is conserved. This is the well-known law of conservation of matter. And as you'll see in a moment, this one is related not only to scale, proportion, and quantity, but it's also related to a different cross-cutting concept, which is matter and energy. So this example reveals another interesting thing about cross-cutting concepts, is that often if you're at the point where you're ready to communicate to kids about cross-cutting concepts, there's a number of choices that you can make. that they lend themselves, many of the performance expectations lend themselves equally well to 1, 2, or 3, or even 4 different cross-cutting concepts. And we'll get to a little later what choices you might want to make in terms of which cross-cutting concepts to teach. Let's go on to the next slide. And if I'm right, I'm trying to predict which one's coming up. No, I'm wrong. This one is systems and system models. So the example here is that students are able to use a model to describe that animals receive different types of information through their senses, process the information in the brain, and respond to the information in different ways. Now, the drawings you see look a little complicated at first, but the idea is that the top illustration is that we have these nerve cells, and they're connected. And the way we think and the way we interact with the world around us is that signals pass from one cell to another. So in the lower example, you can see a finger touching something. That perception then, that feeling then goes to the brain, or to the spinal column, actually, in this case, if it's something like a hot flame, or it might be a tack, actually, that he's touching. Can't quite see it from here. Saying, ouch. And immediately the message goes back again to cause a muscle to move, and the finger retracts quickly from that feeling. So the idea is that if you only think in terms of the content of the core idea, that that we have these nerves and tissues, and they interact with each other, you miss the cross-cutting concept that this is a model of the way the human being functions. And the idea of a model appears everywhere in science. So you have a model of the way a car functions, the model of the way a tree grows. Basically, science boils down different ideas and explanations to models. And what we teach when we teach students is not the real world, because it's too complicated, but we teach models. And as students develop really flexible, usable models about the world, they're able to understand all sorts of different phenomena. Associated with models in particular is the idea that they have limitations. So a model will model only some aspects of the world, not all of the world. So there are complications that come in. And sometimes models are adequate, sometimes they're inadequate to understand a particular phenomenon. So again, with each of these cross-cutting concepts, there's a lot to learn about the cross-cutting concept, not just how you use the concept to understand some aspects of the world. And part of the reason for teaching kids about the cross-cutting concepts is we can help them better understand these very powerful ideas about thinking about the world. So you can call it meta-thinking in a way, but the more students understand these cross-cutting concepts and how they function, the easier it is for them to understand the next topic that they're going to be studying in science. And this idea of coherence among the different science fields is a really, really important part of the framework in the next generation science standards. So let's go on to the next slide, get into the next cross-cutting concept, and I think this one coming up probably will be, if I'm right, energy and matter, yes. So again, energy and matter connects the one that we saw a little while ago about conservation of matter. But in this particular case, it's in some sense two different cross-cutting concepts in one. This particular example is really related to mostly to energy. So students are able to use evidence to construct an explanation relating the speed of an object to the energy of that object. But energy generally interacts with matter. And so that's why they're paired. So in this particular case, this boy was playing soccer, and somebody kicked that ball with a whole lot of energy, and it broke the window. So here's the idea of energy interacting with matter. And usually the way we understand energy is through its interaction with matter. Whether there are calories in a candy bar and the matter that it puts, that adds to our bodies, because that if something is too energy rich, it needs to be, as food, it needs to be converted to some sort of, stored in some sort of chemical mass, which is fat. There's all sorts of interactions between energy and matter, and that's why they're paired here. So let's go on to the next one. We have 2 more to go. Okay, structure and function. So another way that scientists will think about, scientists or energy engineers certainly will think about anything they're trying to design, is that every structure and function go together. Every structure has a function, and if you want to have a certain function, it requires a certain structure. So, and probably the most fundamental idea is that if you want a building to stand up and not collapse, it has to have certain structures, and you can figure out what those structures are. In the case of science, in this case, understanding how a bee pollinates a flower has to do with the way the structures, both of the bee and of the flower, interact. So this example, students are able to construct an argument that plants and animals have internal and external structures that function to support survival, growth, behavior, and reproduction. So a way of understanding organisms is to understand their structures. And their structures are keys to the kinds of functions they have that enable those organisms to exist in the world and to interact with other organisms. Sort of the quintessential interaction here is the bee and the flower, but there are many, many others. So let's move on to the 7th core idea. All right, stability and change. You can't actually think of science without stability and change. And in this example, students are able to represent data in graphical displays to reveal patterns of daily changes in the length and direction of shadows, day and night, and the seasonal appearance of some stars in the night sky. So in order to understand astronomy is really all about those patterns of change. Now remember, the first cross-cutting concept is pattern. How is it different from this one? Well, this one really primarily focuses on temporal patterns. And the idea that some things are stable, yet they change. So, for example, think about the theory of evolution. The idea is that life forms maintain a stability. That is, the offspring are very much like parents. So there's the concept of stability. So a species can be stable over long periods of time, but there are small variations. So there are changes that take place, but the changes are not major, unless the environment changes. And then natural selection really operates on those small changes, enabling some to survive and some organisms to die. So another way to think about it is conservation of energy. Energy changes. It goes from kinetic to temperature changes to electrical changes. So energy can both be transferred from one place to another, and it can be transformed from one form to another. As those changes take place, however, the total amount of energy, if you could capture all of it, stays the same. So it is both stability and change, the complementary nature of those two. That's really important. And of course, you can also focus primarily on change, or you can focus primarily on stability, but it's the connection of these two that I think is especially important in this particular example. So in astronomy, which, as some of you know, if you listened to my earlier webinars, is my favorite subject, It's all about the idea that those changes that you see in the sky, represented by changes on the ground, such as shadows, are the same every day. So they're the same, but they're changes that are stable. And it's that very stability that probably gave rise to the science of astronomy, because without that, you couldn't determine, figure out really what's happening unless you could see those changes taking place on a regular basis. So let's move on. Let's take a look at the next slide. And we're going to move on to some general concepts, or ways, or principles rather, to think about teaching cross-cutting concepts. Now, these are the principles that you'll find in the framework, and I think they're valuable. I don't think they tell you exactly how to teach it. So after I go through these principles, I'll give you my own opinions about how I would teach it as a teacher. And I'll probably give you my middle school viewpoint, because I've been a middle school teacher. I've been a high school teacher as well, but it's somehow my middle school students are the ones that really taught me most about teaching. So I'll give you my recollections of the lessons that they taught me. So first of all, cross-cutting concepts can help students better understand core ideas in science and engineering. And I think I've covered that ground to a large extent, because if you have an idea about, for example, stability and change, evolution is one form of change. It's change, gradual change over time. We often use the word to think about biological evolution, but it also applies just as well to cosmic evolution, or the way a cake will evolve in the oven while it's being cooked. It changes over time. That's really what evolution refers to. And the more we understand about stability and change, the more we can understand all those different ideas that involve change over time. So that's one principle. Let's move on to the next principle. And that is that cross-cutting concepts also help us understand the science and engineering practices. So here's the distinction between a practice and a cross-cutting concept. A practice is something students are able to do. Now, of course, one of the things they're able to do is think about the world around them. But the practices are really pretty specific in terms of ability to analyze data, for example, or apply mathematics, or to argue from evidence. The core ideas are ideas about the science, about the world, or about engineering. So they're not so much what students can do as how they think about the world around them. And they go together, they connect together very, very closely to those practices, because the core idea to some extent gives you an idea of what practice you need to apply. So if the core idea, for example, is about scale, proportion, and quantity, you're going to need to do some data collection and analysis. If the core idea is about cause and effect, then you're going to need to be able to construct an explanation to understand that cause and effect. So in a sense, I would say that not only do the cross-cutting concepts help students better understand the practices, but the practices also enable students to realize or apply the cross-cutting concepts. That's why they go together so well. And again, you'll go crazy if you try to assess them separately. That's what the performance expectations are for. They're a set of ideas all together about what students should know and be able to do with a core idea. So let's go on to the next principle. Okay, repetition in different contexts will be necessary to build familiarity. Okay, this is the most important idea about teaching cross-cutting concepts, because they aren't cross-cutting if they aren't learned and applied in many different contexts. So initially, the idea is to expose students to the cross-cutting concept in many different settings with many different core ideas and many different types of lessons until they start seeing, until the core idea emerges from the context. eventually, and you don't want to wait too long either, but you want students to then come up with their own applications of those cross-cutting concepts so they can begin to apply them in the world. Let's move on through the rest of these principles, and I'll share some ideas about why I think this is probably one of the biggest challenges for teachers. Cross-cutting concepts can provide a common vocabulary for science and engineering. So an example I already gave, for example, was about a form and function. You want to be able to always design something that will work, whether in particular in architecture or building a bridge. Obviously, the form is going to have a lot to do with how well the bridge functions, how much weight it can carry, how well it can withstand buffeting from winds, and so forth and so on. And of course, form and function we also talked about in terms of animals and organisms and how they work together. So both the scientist and engineer will be talking about their world in a very similar way. Makes it easier for the engineer to apply scientific principles and for the scientist to think in terms of the way an organism functions as a device, as a thing. I think one of the best ways to see that connection is through biomimicry, or biomimetics is the more accurate term as far as engineers taking ideas from the natural world, because there's a set of activities called biology in a box, for example. One of them has to do with skeletons, from skeletons to bridges, is I think the activity name. And you think about the way a skeleton functions to enable an organism to move and to stand erect, and to hold all the various organisms and pieces together as the person moves. But those shapes are similar in some ways to bridges, and engineers can be inspired by the natural world. Engineers and scientists need to work together to solve problems. So, so the cross-cutting concept of form and function in this case can give them a common language. But it's also similar to cause and effect. I mean, engineers need to talk about cause and effect as well the scientists do. So one of the themes of some of my presentations has been that everybody does science and engineering. They're two aspects of the world. Yes, it's true that there are professional scientists and there are professional engineers, but even professional engineers do science, and professional scientists also do engineers. In fact, often most of their time is spent doing engineers to make their equipment work. So that common vocabulary is a way for them to talk to not only for science and engineers to talk to each other, but for kids to see how science and engineering are related, but how they're different because the concepts are applied in different ways. Let's go on to the next one. And I think we're getting to the end of our list of principles here, but we have another one. Okay. I think I've emphasized this one enough. They should not be assessed separately from practices or core ideas, and in fact, they really can't be. They're not very meaningful if you try to take a cross-cutting concept out of any context. So that's why the performance expectations are really the place to focus when thinking about assessing student ideas. Next slide. Okay, one more. Performance expectations focus on some, but not all, capabilities associated with a cross-cutting concept. So I think we've seen before. So for example, I think scale, proportion, and quantity. Well, the performance expectation might have to do with measurement and data analysis, but it wouldn't necessarily have to do with scale. Scale, in this case, I'm thinking about as far as, you know, a ratio or proportionality, a scale drawing of a house, for example, or what happens when you scale up organisms and how their needs change, or how you scale up a cell, and how how organisms of different sizes have different, for example, ratios of volume to surface area. So any given performance expectation will usually focus on one aspect of a cross-cutting concept, but not on the concept, but on other aspects. In order to really teach a cross-cutting concept well, it's important to have several performance expectations that are related, and students can begin to see the different aspects of a core concept, cross-cutting concept. Let's go on to the next one. The nature of science is sometimes included as a cross-cutting concept. So the list of 7 cross-cutting concepts that I showed you earlier on that you'll find in the framework has been augmented in the next generation science standards. When you look at the standards, you'll see a page. And at the top of the page is a box. And in that box are the performance expectations. Below the box are 3 columns. These are, you might think of it as a building on top of 3 supporting columns. The left-hand column is the practices that are related to the performance expectations. This central box below the performance expectations are the cross-cutting concepts that are displayed on the top of the page. And on the right side are the cross-cutting concepts. In addition to those 7 cross-cutting concepts, of which you'll find only 1 or 2 or 3 identified for each set of performance expectations, for a reason I'll describe in a moment, that it's important to focus. There are also some ideas about nature of science, such as science is tentative. Science can change over time. Our core ideas can change over time as new evidence is gathered or as old evidence is interpreted in different ways. So these ideas about science and the way science functions are a little bit different from the cross-cutting concepts, but that seemed to be a good place to put them because they, too, cut across all the different sciences. 2 more ideas that you'll find in that right-hand column are that science and engineering are interactive. Science helps engineering advance. Engineering helps science advance. Can't imagine doing science, astronomy without a telescope, or biology without a microscope, for example. So that interaction is also cross-cutting across virtually all fields of science and engineering. And finally, that science, engineering, and technology have impacts on society and the natural world. And they, in turn, have impacts on what scientists and engineers can accomplish. So these ideas, too, cut across. So that set of ideas you will find in that right-hand box as a way of thinking about, or an opportunity for teaching students about the cross-cutting ideas that exist in that particular set of performance expectations at the top of the page. Let's go on to the next slide. Okay, this is also an important idea, that learning progressions exist for cross-cutting concepts, just as they do for practices and core ideas. Now, there's an appendix for cross-cutting concepts. The next generation science standards has 2 volumes now. One volume is the standards themselves. Another volume is chapters or appendices about the various aspects of the next generation science standards. There's one about practices, one about core ideas, and one about cross-cutting concepts. In that chapter, you'll find some tables that describe what each of those 7 cross-cutting concepts looks like for K2, 3, 5, 6, 8, and 9, 12. Obviously, older students can deal with much more sophisticated ideas of those cross-cutting concepts. So curriculum developers, teachers, administrators, it's really valuable to look at those appendices. And when thinking about cross-cutting concepts, it's really valuable to look at what is expected for students of a given age. So yes, they all apply for all ages, but the level of sophistication is really quite different. Let's look at the next slide, please. Okay, so now we get to the meat of the webinar today. How do you teach it? So I like to begin with an example. So imagine you're a 5th grade teacher, and you have finished units on physical science, life science, earth and space science. You want to introduce a cross-cutting concept. Now, I believe I'm a card-carrying constructivist, so I believe that it's important to communicate the ideas before you have the students think about and be very explicit about those ideas. So they already have the building blocks to think about cross-cutting concepts. So I want you to look at the next slide and see the ideas that are included at the 5th grade level. Now, one of the advantages for elementary teachers is that the next generation, by the way, go ahead and shift the slide. Okay. One of the advantages of elementary teachers is that the next generation science standards are grade by grade. So you really have a plan for what the ideas are that you're expected to teach that year. And it's been intentional that that at least 2, if not 3 or 4 different disciplines are taught every year, because it gives an opportunity to teach cross-cutting concepts. Now, I'm going to let you read and think for about, maybe 2 minutes. 2 minutes seems like a long time in a webinar. But I think it's really important to give you a chance to really get your head around this. Read each of these 3 performance expectations, all that are expected for a 5th grade teacher. One for physical science, life science, earth and space science. So imagine these as 3 different units. And think about which of those 7 cross-cutting concepts would be the best way to help students see the connections, see why all of those really represent science. So I'm going to be quiet for about 2 minutes and let you look at those and choose one of the 7 areas. Write it down so you've made a commitment. And I'm timing it as of now. I'll let you look at my sleeping cat while I do that. Okay, so I'm going to go on to the next slide to show you my thinking about the best connection, and let's see how well it connects with your choice. So keep in mind there's no single right answer. As I hope I've illustrated before, some different cross-cutting concepts can unite these ideas. I picked energy and matter because in the first one, the physical science performance expectation, that's really all about conservation of matter. That no matter what changes matter undergoes, matter is not destroyed or created or nor destroyed. Except, of course, for nuclear reactions, but this is the 5th grade. And then life science supported an argument that plants get materials they need chiefly from air and water. This is really photosynthesis at an elementary level, and the idea that the plants don't get their tissue primarily from the soil. It's a common misconception that plants soak up nutrients from the soil, and that's how they get material to the tissue to grow. It actually comes out of the air. It's carbon in carbon dioxide in the air that becomes the carbon in their plant tissues that makes up the great majority of plant tissue. And so that's, again, something to do with matter. And then in the third one, the amount and percentage and distribution of water across the planet is another thing about matter and the way matter is distributed. The first one probably relates more to both matter and energy, the combination of the two. The other two primarily are concerned with matter, although actually photosynthesis involves energy as well. You don't get photosynthesis without energy and matter. So what I would do at this stage is, as I was planning my 5th grade curriculum, if I were, again, teaching the 5th grade, I would, at the beginning of the year, think about all the things I need to teach. And I would pick 2, at most, 3 cross-cutting concepts that I would teach during the year. And I would wait until I've taught it in at least 2 contexts to bring it up. And then bring it up again after teaching another subject, calling the kids' attention to it, and then asking the students to start using their own creativity and thinking of ways that cross-cutting concept relates to anything else in their lives. Because the important thing is, unless they creatively think of ways that cross-cutting concepts will apply to something meaningful to them, it's not going to stick. They aren't going to remember really what it means or how it's used. If this is done every single year, not just through the elementary years, but through the middle school years, by the time students get to high school, they will at last know about these ideas. Now, here's why they're difficult. Meta-thinking, thinking about thinking, is challenging. It's not easy. There is an interesting study done a number of years ago. Hello? Okay. Sorry about that. There's a number of studies done a number of years ago by Sue, who was then an evaluator at the Exploratorium of San Francisco. And the exhibit was all about these cross-cutting concepts. They were called themes at the time. And this particular one was about cycles. And there were all sorts of different cycles in the exhibit. There was life cycles, for example. There was the cycles of astronomy, of the moon phases. And in the exhibit was actually a bicycle. Sorry, that's my cell phone I have to turn off. Okay. So there was a bicycle representing the idea of cycle. And there was signage on the exhibit to communicate the idea that this exhibit is all about cycles. Now, there are very different subjects that were presented. There was astronomy, there was life science, and so forth. But you'd think that visitors would understand the relationship with lots of signage. Sue interviewed the visitors, and very few of them really saw the connection among those. Now, that was a museum exhibit, and typically people will spend at most a half hour, 45 minutes at a museum exhibit. Teachers have much greater opportunity to teach students units of study, opportunities for homework assignments, chances for small group and large group discussions. So there really is a good opportunity either in schools and also in after-school programs to communicate these cross-cutting concepts. Getting students to think about these ideas, I promise you, will be challenging, but very rewarding, because what it will do is it will help students realize that science is a coherent set of ideas about the world. It's very, very easy for science teaching to become fragmented. So kids go to school and they learn about weather, they learn about animals, they learn about astronomy, they learn about the weather. It seems like they're all different subjects. Of course, they're all taught in science class, so they're all science, right? If students understand why they're all science, they will really learn something very fundamental and important about science and about engineering, how all these ideas are connected, and their ways of thinking about the world. Because when they leave school, what's important is not what they remember about weather or what they remember about animals or other topics. What's important is a new way of thinking about the world that will help them solve problems. And heaven knows there are going to be problems in our kids' future. Think about the world population. We're 7 billion plus now. Back in, there were half that number of people back in 70 when I was a young man. And by 2050, there might be as many as 9 or 10 billion people on the planet. But we've already we have farms in just about every arable part of the world. So how are we going to feed all the people of tomorrow? How are we going to have fresh water? How are we going to maintain an atmosphere that's breathable? To say nothing about going into space and understanding where we are in the universe as a whole. So students are going to need to be able to think about these issues, solve real problems. Cross-cutting concepts, practices, are some ways of doing that. That's why it's so important. So let's return to the question of teaching. And I'm going to give you another set of three three performance expectations. Let's go on to the next slide. We're almost near the end of our webinar. So here's another challenge for you. And I'm going to give you a minute now to think about this one. Read through the three performance expectations. This is at the 4th grade level now. And think about which cross-cutting concept you would choose to help students see how all of these are science. Okay, place your bets. Write down 1 through 7 to indicate how you would teach this before I go on to the next slide. Okay, Ella, next slide, please. So I chose those, a set of 3, because there are several really good practice. So let's take cause and effect, for example. So in the first one, objects are colliding. Obviously, that's a cause, and there are immediate effects. I mean, think about cars colliding, or 2 air masses colliding, bringing about conditions for tornadoes. In the next one, animals receive different information through the senses. So again, you prick your finger and you pull it back immediately. There's a cause, there's an effect. And the last one is about weathering. Well, how do things weather? How do rocks weather? Why do they break down? It's because of the effects of heating and cooling of water that gets into cracks, wind, all sorts of erosion effects. Cause and effect would work perfectly, but so would systems and system models, because in each case you can build a model of what's going on. In each case there's a system of interactions, and it's understanding, and you need to build a simplified model to know what's going on in each case. Collisions of objects, for example, you've got to really think about a very simple model to understand, is it momentum that's being conserved, or energy being conserved as well? What sort of collision is it? So use Simplified to understand. Same thing with a model about senses and information processing. So simplified models help, and understanding the system as a whole helps you understand that phenomenon. Energy and matter. They're all about energy and matter as well. In fact, most things are about energy and matter. But you need to decide if that's a good way to unite these. And again, structure and function can also unite these beautifully. So as a 4th grade teacher, at the beginning of the year, I would choose 2, 3 different cross-cutting ideas and emphasize them through the year. Now, I would also get together with the other teachers in my school. If I were an elementary teacher, we would be talking K-5. Middle school, 6-8. But if your school is K-8, then you want to all be talking together. Now, kids, of course, move from school to school, but to the extent that they are going to be in your school for some time, it's a really good opportunity to think about how you will introduce these core ideas little by little. Kindergarten level, you might want to just start with one, or maybe two. And then over the years, you want to add a one or two new ones, and then be sure to reflect the earlier ones from the year before or the year before that. If you get that connection among teachers of the different grade levels, you really begin to develop a deep understanding over time of those core ideas. This is much more than a short visit to a museum exhibit. This is a real chance to to build coherent curricula. And what's going to tie together are those core ideas to help students really see the way scientists and engineers think. So we have just a few minutes left for questions. So do we have any questions yet? Or if not, please go ahead and write in some questions. Ala, do we have any questions?
There's one question from Dwayne Summers. He wants to know if we'll be able to get a copy of the webinar. Dwayne, the answer to that question is yes. We're going to send an email as a follow-up to this webinar, and that email will contain a link to the recorded session.
Let's show the resources slide, which I think is the next slide. One after that. Questions we know. Okay, so what I'm just have shown you here is both the framework, which is a very important document. It's, by the way, while I'm talking, please write in any other questions you might have. The framework from the National Research Council really is the vision for next generation science standards. And then the appendix that I referred to was Appendix G, and you can download the whole thing for free online, or you can purchase the materials directly from the National Research Council of the National Academies Press. Again, Science for All Americans is one of the best books in my collection. It's a wonderful read, and the chapter on themes is really kind of sets the tone for cross-cutting concepts. Do we have another question yet?
No, there are no additional questions.
I know I didn't answer everybody's questions. While you're writing in some other questions, I want to again point out that probably the least understood, the area for which there is greatest opportunity to develop new ideas is how to teach cross-cutting concepts. It's thinking about thinking, so it's a more challenging area. But even young children can think about their own thinking. And I really encourage those of you out there who are interested enough to listen to today's webinar rather, to come up with your own ideas and publish them. You can publish them online. You can publish them through NSTA's journals to share those ideas, because we desperately need help in figuring out how to teach cross-cutting concepts. Do we have another question for our last minute? Ala, no other questions?
Yes, there's a question from Dana. She wants to know where she could get links to previous sessions. Dana and everyone, if you go to mheonline.com, there is a webinars tab, and you can get information about where those previous recorded sessions are.
Well, I want to thank all of you out there who were with me for a whole hour, and I will tell you how much I appreciate an opportunity to do this, because these webinars really give me a chance to think through these ideas and in a logical way that I can communicate in an hour's time. And again, none of them are finished. They're all works in progress. The next generation science standards. We're going to be figuring out how to teach these for the next several years. And I look forward to reading your ideas as we go forward. Thank you very much.
Thank you, everyone.